Okay, hello everyone. I'm Asvesta. I'm a PhD candidate at the University of Thessaloniki in Greece. And I'm going to talk about how the peculiar motions can affect the estimation of our cosmological parameters, and more specifically on the deceleration parameter from the viewpoint of a tilted cosmological model, which I'm going to introduce in some minutes. So I'm going to firstly start with something that we all know about. So the concordance cosmological model fit to the observations tells us that mostly 70% of the present matter content of the universe is attributed to an unknown form of unknown form of energy called dark energy, parameterized by the cosmological constant lambda, which is actually the simplest candidate for dark energy, while the rest of it is called dark matter. The lambda CDM model is actually widely accepted by the cosmological community because it fits very well the majority of the observations, meaning data coming from data coming from supernova of type 1a, SMB measurements, and measurements from large-scale structures. However, even if the model fits very well the observational data, it lacks a physical interpretation. So in order to explain better the data, several alternative cosmological models have been proposed using different forms of dark energy, or even abandoning Friedman FLRW background metrics. Another motivation of our tilted model is the fact that the large-scale peculiar motions are not considerably taken into account, and there is, till now, no robust analysis of the peculiar motion effects at at a great redshift range. So the tilted cosmological scenario can, in principle, explain the very recent cosmic acceleration without the introduction of any additional term or abandoning general relativity. So I referred to peculiar velocities, but what are they? They are just the result of the gravitational attraction because of the presence of the surrounding matter distribution. And they interfere to our observations, so because they add up to the Hubble expansion. So what we actually observe is the combination of the cosmological expansion and the redshift due to the peculiar motions. A lot of research has been made the last approximately 20 years on estimating the bulk flows. And here is like a work from Olink and collaborators back from 2011. We're using using supernova data coming from Union 2 survey. They estimated the bulk flow with respect to the bulk flow velocity with respect to the redshift. And here you can see in the blue line the expectation from the lambda CDM. And as you can see, their best fit values exceed the expectation from the lambda CDM. And they even estimate quite large bulk flow velocities, even at redshift at scales greater than 200 megaparsec. So I'm just here present some of the works that have been made on bulk flows, which are inconsistent with the lambda CDM expectations. And the most recent one comes from Watkins and collaborators using the latest Cosmic Flows 4 data, which they estimated a quite large bulk flow peculiar velocity, approximately 400 kilometers per second, which exceeds at large scales. So most of these works actually agree with the direction of the bulk flow, but they disagree with the amplitude and its scale. So here is the time to introduce the tilted cosmological model. So the motivation for this model comes from the fact that no real observer in the universe follows the Hubble flow, but rather drifts relative to it, having its own peculiar motion. So employing general relativity, the tilted model introduces two families of observers. The first family called idealized or Hubble flow observers, who follow just the smooth Hubble expansion, having a four velocity UA, and the other one are the real or the tilted observers, which move relative to the Hubble flow, having their own peculiar velocity VA. In a perturbed FRW universe and using linear cosmological perturbation theory, the relation between the three velocity field is given by this formula, where VA is the peculiar velocity of the real observers measured in the tilted frame. And we assume that they are non-relativistic as indicated by actually the observations. So if we take the special derivative of this formula, we can define the relation between the expansion rate measured in the two different frames, where big theta is actually the expansion, the Hubble flow expansion, which is always positive, while the small theta is the expansion rate measured from the real observers. And here, if you take the time derivative of this formula, we can introduce the expansion rates between the two frames. And you can see that in the absence of any peculiar velocities, the expansion between the two frames actually coincide. And we stick only inside the linear regime when this ratio is smaller than 1. So you can see that any difference happens between the volume scalars and the expansion and deceleration rates between the two frames are only caused because of the peculiar motion effects alone. So as I showed you before, because the deceleration rates differ, we expect to be the same for the measured deceleration parameters. So in the simplistic scenario, in a perturbed Einstein-de Sitter universe, the deceleration parameter which the real observers inside the bulk flow measure is given by this formula, where Q is 1/2 in the Einstein-de Sitter background universe. And this, in pink, is actually a correction term which depends on the scale, where lambda is the scale of the bulk flow. Here we come up with three important remarks. In the first scenario, you can see that in super horizon scales, where the scale of the bulk flow is very large, this correction term is actually, it's not dominant, and the deceleration parameter measured in the two frames coincide, and the peculiar velocities effects fade away. However, the most important remark comes when the size of the bulk flow is not large enough. So inside quite small bulk flows, the two deceleration parameters change drastically, and the difference actually depends on the scale of the bulk flow. So even if this ratio is small enough, the two deceleration parameters differ. And most importantly, the difference actually depends on the sign of the expansion of the real observers. So inside contracting bulk flows, where small theta is actually negative, the deceleration parameter measured by the real observers can become negative, meaning actually that the observers residing inside bulk flows can actually understand a local accelerated expansion, which is only apparent because of the peculiar motion effects, while globally the universe is still decelerating. So this is actually the results of our latest published work, where we attempted to parameterize the volume scalar of the real observers. So in the scenario of in the scenario that the bulk flow locally contracts, which actually allows for the deceleration parameter of the real observers to change sign, we adopted this scale-dependent formula, which actually has a physical motivation, because we expect in large enough scales the peculiar effects to fade away. So this is the parameterization of the contraction rate that measure the real observers, where MP and R are just free parameters of the model. And this is the scale-dependent deceleration parameter when we adopt this parameterization. So how are we gonna actually reproduce? We're gonna actually reproduce the tilted scenario using observations. So we use supernova data, supernova type 1A data, and we have to define the theoretical predicted apparent magnitude, but in the case of the tilted model. So with a little bit of algebra, we defined the tilted deceleration parameter, which depends on the scale, where alpha and B are just the parameters of the model. So this is just a two-parameter model. Alpha actually defines the value of the deceleration parameter now, and B defines the scale where Q actually becomes positive. And DR is actually connected to the line of sight comoving distance through this relation. So these are the two relations. Here is actually the tilted deceleration parameter and the tilted Hubble-free luminosity distance. And having define these relations, we are ready to define the theoretically predicted apparent magnitude, where calligraphic M is just the degenerate parameter, which contains H0 and the absolute magnitude of the supernova. And here we are ready to use our data. So we used the Pantheon compilation, which actually includes some supernova from JLA plus some additional ones from the Parr stars and the Hubble Space Telescope. This is actually the distribution of the supernova with respect of the redshift, where you can see actually the majority of them lie in the redshift region between 001 and 04 or 5. And this is the special distribution of the supernova, which is kind of unevenly distributed. So, and here I'm gonna present our results. So we also fitted the lambda CDM model for comparison to compare our results. And using the MCMC statistical formula, we were ready to extract our best fit parameters, which is alpha, B, and the calligraphic M. So you can see actually that in the case of the tilted Einstein, of the tilted model, when we adopted an Einstein de Sitter comoving distance, so no dark energy, it is our statistical analysis showed that it performs equally well with the lambda CDM model. And here is actually the 1 sigma and 2 sigma of our best fit parameters and their posterior distribution. And this is the evolutionary behavior of the tilted deceleration parameter, where the blue line comes from the lambda CDM model and the red line comes from the tilted model. And you can see that it's actually reproduced the late time acceleration, and it actually changes from an acceleration to a deceleration to a value of redshift which is quite close to the lambda CDM one. Another important prediction of the model is the presence of a dipolar distribution of the deceleration parameter, solely due to the peculiar effects. And here I'm going to present some latest work very quickly, some latest work that have been made on constraining the dipolar signature using supernova data, who used Sorrenti and collaborators used actually the latest supernova compilation Pantheon Plus, and they found a dipole which is consistent to the CMB one, but the direction actually the direction deviates in a high significance. Another work, a very recent one, using again supernova data, found a dipole which actually it's 2 to sigma away from the lambda CDM1. Another work coming from Quasar this time, who used more than 1 million quasars, and they found a magnitude of the dipole which is way higher than the lambda CDM1 at high expectation. And this is again another study using supernovae, but not a recent data set. So we are motivated by their work. We attempted to introduce a dipole in our previously parameterization of our tilted deceleration parameter. So we used the latest supernova compilation, the Pantheon Plus, because of the fact that the Pantheon Plus have a lot of supernova in the very, very low redshift, and we wanted to stick to the linear regime. We did a redshift cut, so we included only supernova. We included only supernova with redshift greater or equal to 001, which actually is about 8 megaparsec. We fixed the direction of the dipole to coincide with the CMB1. So this is the formula of the anisotropic deceleration parameter in the tilted frame measured by the real observers, where QM is actually the monopole, which depends on the redshift, as I showed you before. And this is the dipolar term that we added, where QD is the amplitude of the dipole. This term is actually a vector pointing to the supernova direction. This is the vector pointing to the dipole direction, which is constant. And this is just a function of the dipole, which in the simplest scenario doesn't depend on the redshift, is constant. So we assume that the dipole is constant through the redshift regime. This is just a first work. So I'm going to introduce very quickly the Pantheon Plus. So here is the distribution of the Pantheon with respect to the redshift. Blue are the Pantheon Plus, yellow are the Pantheon, when you can see that most of them actually will have additional supernova in the very, very low redshift regime. And this is actually their distribution on the sky, which we can say that they are more evenly distributed as the Pantheon, the previous sample. Having said that, I have that we had made a redshift cut. This is actually here we can see that the majority of the low Z and the CSP surveys are out of our 1,400 data set. And this is the distribution on the sky of the supernova on the more constrained sample that we use. And these are just our first results. This is the parameterization again of the anisotropic deceleration parameter. The parameters that we fitted are B, the parameter of the monopole, and the amplitude of the dipole. Again, I am saying that the direction of the dipole is constant, is coincided with the CMB1. Even if the amplitude of the dipole is a small one, we can see that actually it's more than 2 sigma away from the lambda CDM. And again, this is the anisotropical distribution of the deceleration parameter with redshift, where we can see that the acceleration happens a little bit later than in the previous scenario. And I just leave you with some ongoing, some work that can be done in the future. First of all, we can just use some different parameterization of the dipolar form. So we can assume that the dipole actually depends on the redshift. We can enlarge the number of free parameters and let the direction of the dipole to vary. We can do a redshift tomography to the data and check in which redshift being actually the dipole can become stronger. And we can also use different parameterization for the local contraction rates, always having a physical motivation on the background.